For today, we would do divisibility. This year, you want to make it to the nationals.
Right.
That's called...
We know that before we didn't really have the concepts of math and the knowledge.
Okay. Have you worked with the factorization of numbers into prime factors and things like that?
I did a little bit at school.
Good. Do you know how to determine the divisors of a number?
Are you referring to the number of divisors or the divisors themselves?
Basically, to say what the divisors are.
Yes.
Perfect number of divisors. And you know the sum of the divisors too, right?
Yes.
First, we need to discuss what complexities are. If I have a code like this, I starts from 1 and it goes up to n I++, could I, for example, let's say that this code has a complexity of O of n because it performs an operations. Agreed. Good. That's the complexity O of n. If I started from 1 and went up to n1 I++, minus 1 I++, and I was doing something here. What is it, for example? The complexity of the code, this one takes it, it's O of n1, but we can round it to O of n. And let's say it's O of n. We're not really interested in how many operations it actually performs. We're interested in the order of the operations. It performs approximately n operations. Agreed. Good. Similarly, we can say that even if I starts from 1 and it goes up to an NP2, the complexity, how many operations does the code actually perform? NP2, NP2. And we can say that this complexity is approximately O of n because it's the complexity O of n. Good. Even if I have NP2, I'll still say it's O of n. If I have, for example, I starts from 1 and I goes up to NP4 minus 3, I++. What is the complexity of the code?
Approximately O of n.
O of n. Very good. If I have the code, I starts from 1. I goes up to n I++, after which j starts from 1. J goes up to n j++.
N at 2.
N at 2, very good. Why? Have you used complexities before?
No, I've heard about them and I haven't used them and I don't really know. Only from these things that I understood.
Okay, up to this point you've understood very well. The complexity of the decomposition, no, displaying the divisors. What complexity does it have?
Well, it uses a single for, so O of n.
The for loop, but where does the for loop start from?
Well, it starts from 0 up to n. From 1, it is possible, and how?
We're not going to start from 0 because 0 isn't a divisor. And if we divide by it, we'll get an error. Good. But have you seen that you can also go up to the square root of n?
Yes, that's the optimized version.
In which you, for example, if you have the number 36 with the divisors 1, 2, 3, 4, 9, 18, and 36. You only go up to 6 and take the divisors in pairs. 1 with 36 forms a pair whose product is 36. Yes. So you know this algorithm.
Yes, I explained it in class.
I did well here. It's not 4 times 6. 3 times 9. I missed a divisor here. 3 times 9, what is it? 27. I missed the divisor. I missed the divisor 12. Okay. So you know this algorithm too, right?
Uh-huh.
Good. And what complexity does this have?
Square root of n.
A square root of n. So, do you know how to break down a number in square root of n steps? Which is quite good, but it can be even better. And today we're going to learn how to break down a number into a root of order. 3 out of n. Do you know what a root of order refers to? 3 out of n.
I mean, the cube root.
Yes. For example, what's the root of order? 3 out of a million.
1,000.
What's the square root of a million?
It's the square root of a million.
It's 1,000 because 1,000 is squared, it's a million. The root of order 3 out of a million is 100 because 100 to the power of 3 is a million. Agreed. Good. So the root is the inverse of the power as a function. Good. Now, there's a difference, not a significantly complex one, but some problems require. We're going to discuss, if I give you the number n equal to factor 1 to the power of e1 times factor 2 to the power of e2, or points times factor k to the power of ek, for example. If I give you the number 36, you're going to tell me that this is equal with 2 to the power of 2 times 3 to the power of 2. If I give you the decomposition of a number into prime factors, let's see what it's equal to. The number of divisors of a prime factorized number, let's see what it's equal to. The number of divisors. Do you think it's the number of divisors of a number like that? For example, 36. has 9 divisors. What are the divisors of 36? We have 1? Not really. I want to express it in another form. The divisors of 36 are 2 to the power of 0, 3 to the power of 0, and the exponent doesn't change. 2 to the power of 0, 3 to the power of 1, 2 to the power of 0, 3 to the power of 2, 2 to the power of 0 times 3 to the power of 3. It's a divisor of it. Try to say, no, it's not. Why?
Well, because 3 to the power of 3 is 9 times 3, which is 18. No, 18, forgive me.
It's 27.
27, I got it?
Yes. The idea is that if I have the exponent 2 here, I can't have a higher exponent for 3, because that means it won't divide evenly.
So the exponent is smaller.
Yes, I will have 2 to the power of 1 times 3 to the power of 0, and this is a divisor for me. And 2 to the power of 1 times 3 to the power of 1, and 2 to the power of 1 times 3 to the power of 2, 2 to the power of 1 times 3 to the power of 3. I said it's not a divisor. What other divisor do I have? 2 times 3 2.
0. 2 to the power of 2, 3, 1, 2, 3, 2, and so on.
Is 2 to the power of 3 times 3 to the power of 0 a divisor?
No. So 3 is greater than...
So these are all my divisors. How many divisors do I have?
9.
9 divisors. The power of 2 can take the value 0. The power of 3 can take the value 0. 1, 2. In total, in how many ways can I combine them? For example, I can have 0 with 0, 0 with 1, 0 with 2. 1 with 0, 1 with 1, 1 with 2. 2 with 0, 1 with 1, 2 with 1, 2 with 2. In how many ways can I combine them?
You're not using factorials for this.
No. The first number I can combine with how many?
2 with 3. The second, top 3 and the last. 9.
If I had P2 to belong to me from 0 to 4 and P3 to belong to me from 0 to 1, how many do I have now? 10. 10. Very good. 5 times 2, right? Yes. Good. And then we go back to this problem. If the first number is raised to the exponent e1, it means that the divisor can be of the form f1 to the power of 0, f1 to the power of 1, and so on, up to k. f1 at e1, that can be the first value. Okay. Already, if it's to the power, it's plus 1, it's no longer good. How many values do I have here?
E1. Plus 1 values.
E1 plus 1. How many values can this take?
E2 plus 1.
E2 plus 1. This one.
Okay. Plus.
So then, what is the number of divisors, I wonder? I'm going to take anything from this, anything from that, anything from all of this, and anything from this.
So it should be 1 plus 1, in addition to being 2 plus 2, and so on up to ek plus 1.
Yes, very good. But you said it's 2 plus 2, but it's 2 plus 1.
Ah, I got confused. Yes, you said very well. Now I realize.
Exactly. And this is the number of divisors? Yes. We'll discuss it right away. The sum of the divisors and the product of the divisors. It's just that these are a bit more complicated. And now that we know the number of divisors, let's see how we can take a number in this form. How do we factor a number in this form? If I give you the number 72, how do you factor it in math?
Dude, you divide it by 2 first.
Yes. You get 36.
Again with 2.
Yes.
Again with 2.
Yes.
Now, with 3.
Yes.
One more time with 3, and that's it.
And 1 yes. Yes. Good. So then I can write the following code. To break a number down into its prime factors. I read the number that I want to break down. I have a divisor that starts at 2. As long as the divisor is less than or equal to n, I will have an exponent. Not if n is divisible by the divisor, which will be a prime number, I will have an exponent that initially is 0. As long as the number on is divisible by d, I divide it by d and increase the exponent. And then I will say here, because I have d to the power of e, and in the end I need to increase Mr. So then, for example, if I say the number 72, it's 2 to the power of 3 and 3 to the power of 2. That's good. If I say the number 18, it tells me 2 times 3 to the power of 2. So we managed to break down a number into its prime factors. Yes, good. What complexity does this have? For example, if I give you the number, in the worst case, how far can d go? Let's think about what happens, for example, for 7. For 7, what does my algorithm do? Is it divisible by 2? It's not divisible by 2. Is it divisible by 3? It's not divisible by 3. Is it divisible by 4? It's not divisible by 4. By 5? It's not divisible by 5. By 6? It's not divisible by 6. And I got to 7, and it is divisible. In the worst case, how many steps does my algorithm take for a number? ODN. So we have the complexity ODN right now. I haven't gotten anywhere. We have the complexity ODN, which is worse than what you typically know how to do. To determine the number of divisors, for example, we can instead go up to the square root of it. And let's see what happens now. If I give you the number 27, it tells me it's 3 to the power of 3. Let's go. If I give you the number 18, 2 times 3 to 2, I'll go. If I give you the number 7 and it doesn't tell me anything, but it should be 7 to the power of 1. And in the case where we go up to the square root, in the end, we have the case where we end up with something. And if we end up with something, this something we've ended up with is a prime number to the power of 1. And then I'm going to say C out n to the power of 1. So n, well, let's think about it. Let's see if it works the first time. Will it work for 7 now? Yes. Does it work for 18? It works just as well. It works just as well for 27. It works for 101, which is a prime number. And then we have the square root complexity of it. Okay. Let's think about why if we go up to the square root of a number, in the end, we'll be left with a maximum. A prime number to the power of 1? Well, let's say that a and b are 2 prime numbers. Prime, and a is less than b. And let our number m be a times b. What does the algorithm do? It goes up to the square root of a times b, which we know is greater than a and less than b. Do we know this? We know this. Good. And so we go smaller, equal, just to put equal, but it's clearly smaller. We go smaller than the square root. So we take these numbers, and in the end, we'll be left with b. If our number is in the form of a squared times b to the power of 5, all we want to detect is a and b. So we basically, it's clear that a squared is less than the square root of a squared. It's smaller than that, but I think this thing is even smaller than b. But the idea is that in this case, we go up to here and take both of them. So, in the worst case, or if we have 3 numbers, let's see 3 prime numbers. A is less than b, less than c. A is clearly smaller. In general, I think that's the relationship, ABC. The square root of ABC. And yeah, probably. I mean, not for all numbers. If they are distinct, it's not necessarily for all numbers. C can be on the left or on the right. But B is clearly here. The square root of ABC. Why is B clearly here? Because we multiply B by something greater than B. And besides that, we multiply it by something else. So this square root is clearly larger. And what could it be here? We're going to take all the numbers up to this point, and we'll only be left with C. And you can also keep examples, and you'll realize intuitively why it works. But the idea is that, in the end, we're left with 1. We can't stay that way. We can end up with a prime number to the power of 1. And that's why we need to give more. This C out at the end? Okay. So then if I want to, and right now we're at the square root of it. So right now we're doing what we can do otherwise anyway. But let's say I want to calculate the number of divisors. The initial number of divisors is equal to 1 that we're going to do in multiplications. At the moment I find 1, a prime factor to a power is, what am I going to multiply the number of divisors by? For example, here I found 2 to the power of 3. 2 equals 2, it equals 3. How many did I say the number of divisors is? Is this new? Yes. So then what do we multiply it by here? The number of divisors
with plus.
It's plus 1. Does the code work? Well, let's see. For example, I say here a BXLN. And at the end, I want to print the number of divisors. Let's try for 36. I said it has 9. It works. It tells me there are 9. Let's see for 27. It has 4 divisors. 1, 3 to 1, 3 to 2, and 3 to 3. It works. Let's see if I tell you now 7, and it tells me it has 1 divisor. How many divisors does 7 have? It has 2. It has 2 divisors. Where is the problem in this code? The fact that we multiply It's good that we multiply, but we don't multiply everything we should. We have something where we don't multiply. We should multiply in one place and we're not doing it. And we also talked about this 7 before something wasn't working.
So we should do everything if n is greater than 1.
Yes. What should we multiply the number 2 by?
Let's multiply its plus 1
How much?
with its plus 1.
Yes. And how much is e? By the... You said that e is 1, but I didn't hear you. No. How much is e? 1. 1? So then, what do we need to multiply here? Let's multiply just by 2. Okay. Yes. And now it will work for 7 too. For what other numbers didn't it work? For example, it didn't work for 2 times 101. This one tells us that it has 2 divisors, but it actually has 4 divisors. For example, it gives you n as 2 to the power of 2 times 3 to the power of 1. Okay.
I mean, yeah, it gives you a fire for reading.
Yes. It's just that they are given to us 100,000. About numbers, each number x is a number up to 1 million. And the powers go up to 10 to the power of 9. That's why we want to display the answers, the remainders when divided by 10 to the power of 9 plus 7. And in this case, we will want to calculate, for example, things like 101 to the power of 1 billion. After that, we need to calculate 3 to the power of 1 billion and also calculate 2 to the power of 1 billion.
Then
it becomes very slow. And for that, we want to calculate, this is fast. And let's think about how we can, for example, calculate a number x to the power of 8. We can take the numbers from 1 to 8 and keep multiplying by x. Answer or is equal to x, right? Or is equal to x. But that's very slow and we won't do that.
we need to do something with the radical.
It's not really in the radical, it's in the logarithm.
Have you heard of logarithms? You know about them, but you don't really know.
Binary search has, for example, logarithmic time because it keeps dividing the interval in 2. And I'll say how we do that. Let's say we know x to the power of 4, x to the power of 8 is just x to the power of 4 squared. To calculate x to the power of 4, we will want x to the power of 2 squared. For x to the power of 2, let's say it's x squared. So basically x to the power of 8, x to the power of 2, everything. To the power of 2, everything to the power of 2. And now, instead of how many operations? Instead of 8 operations, we do 3 operations. Let's see. For x to the power of 10, x to the power of 10, let's say it's x to the power of 5 squared. X to the power of 5 is an odd number, so I'll say it's x times x to the power of 4. For x to the power of 4, I'll say it's x to the power of 2 squared. What is x to the power of 2? I'll say it's x squared. What functions have you worked with?
So let's create a function with a frame.
Yes, have you done more?
Yes.
Okay, about recursion. Did you hear?
I mean, when the function. Yes.
Call her.
Call her. How would you know?
Have you used it again?
No, but I've heard about it.
Okay. For the 9th grade, it's not necessarily required for the Olympiad. This is what I explained to you. Here it's called exponentiation. Fast exponentiation. I'll send you the link to the problem in the chat. And let's take a look at PB info about fast exponentiation, and I'll also send you the article. As far as I know, it's in 9th grade, but I'm not exactly sure. Expo isn't, it's in 10th grade. I wonder, fast exponentiation of times. And we have the function that would normally calculate the power. So the product is equal to 1, and we multiply it by a n times, because I want it to the power of n. Something else, I can say, that is, a to the power of n is 1, if n is 0, if n is odd, it's equal to a times a to the power of n minus 1. And if n is even, it's a to the power of n divided by 2, all squared. For example, for 2 to the power of 25, it is calculated as follows. 2 times 2 to the power of 24. 24 is calculated as 2 to the power of 12 squared. 12 is 2 to the power of 6 squared. 6 is 2 to the power of 3 squared. 2 to the power of 3 is 2 to the power of 2. 2 to the power of 2 is 2 to the power of 1. And 2 to the power of 1 is 2 times 2 to the power of 0, which is 2 to the power of 0 equals 1. Then, in reverse order, I don't know what it does. So the function, if n is 0, returns 1. If n is odd, it returns a times the power of a to the power of n minus 1. Otherwise, it returns power p, or p, and p is a to the power of n minus 2. Okay, did you understand that? All right, we also have the non-recursive version that works like this. And makes sense, but I'll explain how this works step by step. So I want to write it down for the first time. The recursive version, but I don't think we get partial points. And the product of the numbers is calculated a bit more difficult. But come on, there's a problem on PB info. With this, let's see how it's done. For example, this one that says it's difficult, Mocha wants to post a problem of difficulty. B, it's the remainder of a divided by the power of b modulo, this number. And I'm going to say it like this. Even though we're reading from files, we want 2 to the power of 4, for example, we'll have a modulo, this number will have a to the power of b. And I want to print power from a to the power of b, let's say. And the power function from a to the power of b is as follows. If different from b, so if b is 0, we return 1. If b is odd, b modulo 2 is 1, we'll return a times power of a to the power of b minus 1. A, or a to the power of b minus 1 modulo 1. Okay, I have n. I read n, and I read n numbers that I want to factor. I want to factor the number x, and I'm reading it. And I start with a d equal to 2 as long as d times d is smaller. Equal to x, if we have a result equal to 1. In the end, we print the result, and it has to be on the same line. Or, if x is divisible by the number d, we automatically know that we have a prime factor to the power greater than or equal to 1, so we multiply the result by 2. And now we want to get rid of all the factors of d from x. X is divisible by d. And that should work. Not really, because in the end, if x is greater than 1, we multiply the result by 2. Correct? Yes. Okay, I forgot to increment d. Fardo. Let's see if it works. Okay, it worked. So it's not a gender issue. I'm going to look for the homework now. I'll maybe leave you a problem that doesn't involve a radical. You still have a few problems left. But there are also some where it doesn't involve a radical, and you have to take the cube root, and you know it exists anyway. And there are some problems, but they are difficult problems. I don't really know if they exist on PB info, where you need to use a logarithmic decomposition of n, which clearly makes a difference there, because the log of 10 million is approximately 23 in the log of this radical, which is 1000 or something, 1000 and a bit. 23 in the log of this radical, which is 1000 or something. 1000 and a bit. 1000 and a bit. That definitely makes a difference. And I'm sure these are some problems. It's just that they are harder, and I didn't want to jump straight to the first session. But if you don't find any, you'll only have decomposition problems in the homework, in factors, in prime factors under a radical.